Would you believe me if I told you that one of the most powerful acids we've made, one that is stronger than battery acid by several orders of magnitude, is also the gentlest acid? And what if I told you that the same element that helps that acid be as strong as it is was traded along the Silk Road in the form of an incredibly useful powder? There's also a good chance that the same powder is in your laundry room right now. That powder, of course, being borax, and the element that plays a key role in borax and our superacid is boron, element number 5. Hello and welcome to Meet the Elements, the series where I look at the stories of humanity through the lens of the periodic table. Today, we're taking a look at boron, a surprising element that has played its part throughout human history. But before we get started, make sure you subscribe and hit that notification bell so you don't miss future episodes of Meet the Elements. And now that you've done that, let's talk about boron. Long before anyone called it boron, before anyone really knew what an element even was, merchants along the Silk Road were spreading it throughout the Arabian Peninsula. The substance went by a few names. Originally known as tincal, Arabic alchemists called it borax, which eventually became borax, a white, chalky crystalline powder originating from dried lake beds in Tibet. And it was incredibly useful for several different applications, but no one knew why it worked so well. They just knew that it did. Metallurgists and goldsmiths found an exceptional use for borax. When you are trying to join two pieces of gold with a solder joint, for example, and the solder isn't holding, borax will get it to stick. Apply borax to the metal surface and add heat, and it dissolves the stubborn oxide layer sitting on top of the metal. That invisible film of corrosion, the thing preventing a clean bond, dissolves away. Borax was the first flux, a metallurgical secret ingredient used well before we had the chemistry to explain it. Artisans of all sorts used borax, glassmakers, jewelers, ceramic artists, because it could help get things to actually fuse together. What borax actually is, chemically speaking, is sodium tetraborate. Sodium, boron, oxygen, and water locked together in a crystalline form. When it dissolves in water, it releases borate ions, which are also found in boric acid. So then when boric acid was found in the hot springs near Florence, Italy in the mid-18th century, that eventually became a main source of borax until American sources were found in the late 1800s. One of the primary sources of American borax? Death Valley. Beginning in the 1880s, teams of 20 mules, well actually 18 mules and a couple horses, hauled borax-laden wagons out of Death Valley and across the Mojave Desert to the nearest rail depot. And with this massive supply of borax now available, it started being used all over the place. Just to name a few uses, the glass in your Pyrex dishes, and a significant amount of chemistry glassware, is made of borosilicate glass. Boron lowers the thermal expansion of the glass, meaning it resists cracking when temperatures swing suddenly. You're probably most familiar with borax in household cleaning products, where it's been used for decades at this point. It softens hard water, can boost detergent performance, and can even work as a mild disinfectant. Boron also absorbs neutrons quite well, which makes it very useful in the control rods of a nuclear reactor, the rods inserted into a reactor core to regulate the chain reaction. And borax can also be used to make slime when combined with PVA glue. This is also a fun science demo for younger audiences, since it's an example of polymerization, the borax cross-linking with the PVA molecules. And that's only a sample of the uses borax has. And that's also just borax, not even boron. Not bad for something that was traded alongside silk and spices. But now let's get into that incredibly powerful acid I mentioned earlier. And to start off, what would you say is the strongest acid we know of? There's sulfuric acid, which would be a reasonable guess. It's corrosive, industrial, and dangerous. After all, it's half of the mixture to piranha solution, something you might have seen eating a piece of chicken whole. But it's not the strongest. So what about fluoroantimonic acid? Well, that's certainly stronger, about 20 orders of magnitude stronger than sulfuric acid. It will corrode most metals, instantly rip apart flesh, and will even eat away glass if it's given the time. But it's technically just a mixture of hydrogen fluoride and antimony pentafluoride. It's not a single compound, so some people like to rule it out as the strongest acid because of that. But the acids I want to tell you about are single component and can be as strong as fluoroantimonic acid. These are carborane acids. The one you'll most likely hear about is chlorinated carborane acid, a cage of 11 boron atoms with a single carbon atom, a hydrogen atom, and then 11 chlorines. They are incredibly strong, also orders of magnitude stronger than sulfuric acid, upwards of a quintillion times stronger. Yet carborane acid doesn't dissolve the container it's in. It's not particularly aggressive towards metals, and it likely won't damage your skin if you were to get a drop on you. But I would still try to avoid it. The strength of an acid really comes down to one thing: how readily it donates a proton, a hydrogen ion. I mean, it's more complicated than that, but I'm trying to keep things simple. The stronger the acid, the more easily it releases that proton. In extreme territory, beyond the typical pH scale, we measure this on the Hammett acidity function, which extends into the realm of superacids. And while we tend to focus on giving away a proton when discussing acids, it's just as important to discuss the other part of the acid left behind, what's referred to as the acid's conjugate base. And the more stable the conjugate base, the stronger the acid. Which brings us to carboranes, and to boron's role in everything. A carborane is a cage molecule, boron, carbon, and hydrogen atoms arranged in a polyhedral structure, specifically an icosahedron, a 20-sided solid, the same shape as a D20 for all my tabletop fans. When you use this cage as the basis for an acid, attaching a proton to the cluster, you get a really strong acid because that carborane base is incredibly stable. It doesn't want to react with anything, and it especially doesn't want that proton back. The proton is fully liberated, and the conjugate base just sort of sits there. This is why carborane superacids are both extraordinarily strong and surprisingly gentle. The strength comes from the donation of the proton, but the gentleness comes from the conjugate base having no interest in doing anything else. And that's the great appeal of using a carborane acid over something like fluoroantimonic acid. Traditional superacids are so corrosive that they destroy their environment. Carborane acids are more targeted, doing what you need them to without causing unnecessary damage. And hey, if any of you have any experience working with these superacids, leave a comment and let me know what that's like. I genuinely want to know, and I've never had the chance to work with one before. And there is one final boron compound that I want to talk about, but I need to preface this section by starting with diamonds, which you might know is a form of elemental carbon. Depending entirely on how its atoms are arranged, carbon can be graphite, the soft flaky material we use in pencils, graphene, a single layer of carbon atoms, or diamond, one of the hardest substances on Earth. And boron nitride is nearly as hard as diamond, and depending on the application, it might actually be preferred over diamond. Boron nitride has all sorts of uses. It can be used as a lubricant when it's a fine powder, it's been used in cosmetics, and it can also be used as a semiconductor, which comes with a whole other list of applications. Boron nitride is also widely used as an abrasive, since its hardness is close to that of diamond. In particular, boron nitride abrasives are great for use with steel, since it's insoluble in iron, whereas diamond, i.e. carbon, is. And I actually used boron nitride quite frequently as a grad student when I was preparing samples for X-ray absorption spectroscopy. The low mass of both boron and nitrogen means it's not going to readily absorb X-rays in the ranges I was working with. I would say boron is quieter than a lot of elements. You don't really hear people talking about boron all that much, but it has done something pretty incredible. Boron has threaded itself through human civilization so completely that we barely notice it. Borax in your laundry room, the carborane acids in a research lab, and boron nitride being used all over the place. Boron is an element we've relied on for centuries upon centuries. And that is element number 5. Thanks for watching. I know I didn't mention everything there is to know about boron. It has so many uses that I was never going to be able to cover them all. So go ahead and leave a comment talking about your favorite use for boron. And don't forget to leave a suggestion for an element you want to see me cover in the future. And make sure to subscribe and hit that notification bell so you don't miss the next episode of Meet the Elements.